So the next topic is going to be revolving around bonding for carbon and how carbon can actually bind itself to other carbons as well as to other atoms. And the theory that we're going to use to explain the way that carbon does this is called hybridization theory. So before we actually go into the theory, I'm just going to kind of cut to the chase and give the results of what we can find in nature, how carbon can actually bond. And there are three main motifs. The first motif that we see is with this example on the left. So an example would be, just methane. So this carbon has 4 hydrogens that are attached, and this kind of bonding motif has a couple of different ways you can describe it. The first is the overall geometry. And the overall geometry is what's called tetrahedral geometry. So this actually looks like a tetrahedron if you tried to connect all the dots and you talked about how these hydrogens would take up 3-dimensional space around the carbon. You can also measure bond angles between this hydrogen and this hydrogen. So if you wanted to measure the angle between these 2 hydrogens, you would find that the angle here is 109.5 degrees. And it's a very specific number that you definitely need to remember for later. And for this tetrahedral geometry, what we would say is you really think of this tetrahedral geometry as with carbon having all single bonds to it. So every single one of these bonds is a single bond. The only thing that's a little weird is that you have these little dashes and wedges right here. And we're going to talk more about what these actually mean in a couple of videos. Suffice it to say for now that these are just kind of describing 3-dimensional nature of the hydrogens that are attached. So you could imagine yourself putting on some 3-dimensional, like some 3D goggles, and you could actually see these hydrogens, how they look in 3 dimensions. But we'll talk more about that later. Another way that carbon can bind is for this following example. So the way you could draw this carbon and hydrogen framework out would be like this. So this is what you would normally think of as having a trigonal planar geometry. And by trigonal planar, what we mean is that this molecule would be flat. You could lay it flat on a table, but you also have this triangle that you could draw if you connected carbon to hydrogen to hydrogen to carbon. So you have this kind of a triangle that you could draw. There's a certain angle that you need to remember for this type of orientation and bonding as well. And the angle between this carbon and this hydrogen, if we measure this angle, this has a very specific angle. It's 120 degrees between this carbon and this hydrogen, and another 120 degrees between this hydrogen and this hydrogen. So these angles are very well known, and it would do you well to remember these for later on. We'll talk about them more in detail later. And so for this trigonal planar geometry, what you normally think of in terms of the bonding for carbon is that this is a scenario where you start to get not just single bonds, but you have a double bond as well. So this is what you would see if you had a carbon to carbon double bond or carbon to some other atom double bond. So the third example would be the scenario with a formula of C2H2, and the way this molecule would look is as follows. So this molecule has its own particular geometry, and we call this molecule linear in its geometry. And this molecule's linear geometry has a certain angle that's associated with it as well. The angle between this hydrogen and this carbon, if you measure this angle, it's actually pretty obvious at this point, I think, but this is 180 degrees between this hydrogen and this carbon. So this is another angle you need to remember. We'll use these later on as well. So for this linear geometry, the bonding that you would normally associate with this linear geometry is this triple bond. So 1, 2, 3 bonds between this carbon and this carbon. So for each of these different geometries, we associate these with different types of bonding. Tetrahedral, you just have single bonds. Trigonal planar, you have this double bond, and linear, you have this triple bond. And in order to get these geometries, the rationale behind how we're actually able to get them comes from hybridization theory. And what hybridization theory can tell us is a little bit of information about these red carbons right here. And again, kind of skipping to the point here, each one of these red carbons has what's called a different hybridization. This tetrahedral carbon has a hybridization called sp3. This carbon has a hybridization of sp2, and this hybridization has, this carbon has a hybridization of what's called sp. And so what we're going to do is talk about how we actually get to these designations, sp3, sp2, and sp. And the way that we do that is by talking about carbon's valence. So if we think about carbon's valence, carbon has a 1s orbital that's completely filled, and it has 4 valence electrons from there. And if we were to fill in the carbon's valence, it would look a little bit like this, where we would have one 2s orbital, and we would have 3 2p orbitals that are ready and willing to accept electrons. And so since carbon has 4 valence electrons, if we were to actually fill in these orbitals, keep in mind that what we're doing is we have actually a y-axis right here. And as we go up this y-axis, we're increasing energy. So energy is kind of going up as we go up this little y-axis. And so 2s orbitals would be lower energy than 2p orbitals. 2p orbitals are higher energy. And the way that we would fill in these orbitals, if they were just kind of sitting there willing and ready to accept electrons, is we would first put in 2 in the 2s orbital, and then that means we have 2 valence electrons left over, so one would go here and one would go here. So this would be the ground state for an atomic orbital for carbon. This actually doesn't work very well if you're actually trying to bond 4 things to a carbon, so like this structure of carbon that we started off with. So if you're actually trying to describe this methane, it turns out that methane isn't really able to be formed utilizing this atomic orbital. This lowest energy arrangement really implies that, these electrons right here should really be a lone pair. And then that means that you really only have 2, orbitals available if you wanted to bond something to carbon. And then this last one's not even filled with anything. So this would be like if you actually wanted to bind one of these hydrogens, you could bind one hydrogen here and one hydrogen here, but that doesn't really explain these other 2 hydrogens. So really the best you could do with this arrangement is this kind of orientation where you have a lone pair and 2 hydrogens, and it turns out that this carbon is really bad because 1, you don't have a full octet, and 2, this molecule, it's a highly reactive species that can't really be isolated under typical lab conditions. So to really describe this sp3 tetrahedral geometry, a couple things have to happen, and that's where hybridization comes in. So the way that the molecule gets around it and the way that we can kind of form a mental model is to pretend that this s orbital is able to combine with each of these p orbitals. So, the s orbital kind of melds with each of the p orbitals. It's kind of like you're breeding Pokemon together, and you get attributes from both the original parent Pokemon to get something new. So once you hybridize all of these orbitals together, the main thing to remember is that when you're hybridizing, you're putting 1, 2, 3, 4 orbitals in, and what you're going to get is 4 orbitals out. So the 4 orbitals that you get out are going to be each sp3 hybridized. So what you're really saying is you're commenting on the composition of each orbital. So each one of these is 25% S and 75% P. 25% S, 75% P, 25, 75, 25, 75. And because you hybridize this with each one of these, they're all the same in energy. They have the same attributes. So what you can do now is you can take those 4 valences and just kind of distribute them along like this. And so now you have 1, 2, 3, 4 electrons that are ready and willing to bond with 4 different atoms. So in this case, hydrogen, 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 and hydrogen. So each one of these single bonds has a specific name. We call these sigma orbitals. And sigma is just somewhat synonymous with single bond. And you'll probably hear me go back and forth. So now what would we do if we were trying to make an sp2 hybridized orbital? As the name implies, what we're going to be doing is combining one s orbital with 2 p orbitals. So at the end of the day, the composition would be 33% s and 66% p. So what we would do is we were going to take one of these and combine with these 2, and then we're going to get 1, 2, 3 orbitals in, and we're going to get 3 orbitals out. And 1 p orbital is just kind of be sitting there untouched. So after we do our hybridization, we're going to have 1, 2, 3, 4 electrons to kind of put in to our hybrid orbitals. And we would put these electrons here, 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 and here. So now, whenever we actually draw double bonds, we really have 3 sp2 orbitals that are being used for bonding. Here, here, and here. These are all sp2, 1, 2, and 3, 1, 2, and 3. And then this last orbital, this p orbital, is being used for the double bond. So this would be our p orbital right here. So sp2, 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 and then the last p orbital is used for this double bond. And if we're going to make an sp hybridized molecule, again, what we're going to do is take one s orbital combined with one p orbital. And we're going to end up getting 2 sp orbitals out, because we put 1, 2 orbitals in. We're going to get 2 sp orbitals out. And the other 2 are going to be just regular untouched p orbitals, p and p. And so just like before, we have 4 electrons to kind of do stuff with, and we're going to put them here, 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 and here. And an example again would be this triply bonded carbon. And so if we wanted to describe where these sp orbitals would be, we could say we could have 1 sp orbital here and 1 sp orbital here, so 2 sp orbitals, and then the other 2 are just regular p orbitals, right here and right here.